All right. Hello, everyone. My name's Amir. Today is the part 3 of our AI workshops for the materials and molecules domain. So today, this initiative is funded by Digital Research Alliance Canada. So thank you to them for funding this project and helping us bring the knowledge to a large group of people. So now I'm starting to see on the LinkedIn group, there's people from across the world. Last time we had one person from Ghana. I think there was one person from Germany who had signed up. So it's nice to see there's starting to be a bit of an international interest for our workshops, etc. So we hope to maybe in the future keep up that momentum. And of course, there's tons of McGill, Concordia, UQAM, UDM, etc. So Quebec and Canada as well. With all that said, I'd like to just give a brief bio on our presenter today, Dr. Alex Hernandez Garcia. He just recently joined the University of Montreal as an assistant professor at DRO and Mila. He is focused on tackling the climate crisis and health challenges. And today he'll be telling us all about GFlowNets, which is started here in Montreal from Dr. Yoshua Benchio. So Alex, take it away.
Whoops. Hello, can you hear me well?
Yes.
Perfect. So yeah, thanks for the introduction, Amir. Thanks for the invitation as well, and welcome everybody. I'm gonna try to share my screen and hopefully it'll go well. All right.
We see it.
Okay, perfect. So yeah, I'm Alex. I'm a professor at Milan, the UDM, and yeah, my work is on machine learning for science. So I just wanted to give a quick note about that and the kinds of things I do and why I'm giving this tutorial today. So I try to work on machine learning research that has applications for science, for scientific discoveries in particular, but not only, things that can have a positive impact on things like climate change, health challenges that are pretty much related. So that means materials discovery for sustainability, drug discovery as well. And something that I find really cool is that there is a very nice synergy between all these things. So the work on drug discovery also informs the work on materials discovery and vice versa. And then the application of machine learning research for the sciences also brings up challenges for machine learning research and informs the way we can do machine learning research, and that's very stimulating. So a lot of inspiration in both directions. So just to give you a bit of an outline for the session today, I will just start with a brief introduction about machine learning for scientific discoveries. Then I'm gonna give you a general introduction to this tool, this framework called GFlowNets. Then I'll get into more details about a particular version of GFlowNets, which is the Crystal GFlowNet, Crystal GFN, which is specifically designed to assist material discovery. And for the second part, we'll do a hands-on tutorial about the GFlowNet library and the Crystal GFlowNet. I want to say a word about the fact that there's a lot of material in these slides, and I did that because I wanted to leave it there for you to explore and check and go back to it at your own convenience. But also I don't have time to cover everything, so there will be some things that I will skip or go a little bit fast. But yeah, I didn't want to remove a lot of things that I find interesting, and perhaps later you can go back to the slides. I don't know if you got it, but the slides are online, so this is the link. You can scan this QR code. Yeah, so maybe I give a couple of seconds in case you gonna scan it or get the link. So everything is online. You can go back to it whenever you like. All right. So First, a little bit of introduction about how we are using machine learning for scientific discoveries and why. And for that, I want to briefly mention how the traditional discovery cycle has worked for many, many years, decades, centuries even. So typically, it works such that there is scientists that have a lot of expertise and come up with ideas, things to try, and then there is a way to check these ideas, to check the hypothesis or the potential candidates if the task is to discover new things. That's called that an oracle, but bear in mind this can be like a computer simulation, wet lab experiment. Really depends on the application, right? And the experiments give us some data, some kind of information in a very broad sense. So data in a very broad sense, information that will inform back the scientists and help them refine the ideas, right? So this works pretty well for a lot of things, but of course it relies on this human expertise. And depending on the application, it can be very time consuming. You probably know very well this if you work in labs or do computer simulations for materials. So that can also be expensive financially. So I'm a machine learning scientist. I see this, I see data here. I was like, okay, we can do something with data with machine learning models. So the first way to introduce machine learning into this loop is by taking the data to train a machine learning model. And then, of course, we can use it for something. One way to use this machine learning model is to test our hypothesis, our queries, on the machine learning model instead of the very expensive oracle. The machine learning model will be much cheaper, but of course, more inaccurate. So we have to be aware of that as well. However, I want to notice something, which is that even if we have a very good machine learning model that is very fast, and this is not the case, we are not able to explore all the possible candidates in certain applications. In some cases, the possible candidates are just infinite. So in terms of conceivable materials, because we are dealing with continuous valued things like atomic positions or lattice parameters of a crystal, it's just infinitely many potential things we could build. And even if we talk about just the potentially stable, some people had said that it's 10 to the 180. There's no time in a human life to do that. Even if you have multiple computers at the same time, this is not feasible. So is this enough? The answer is that potentially no. It could be too slow, especially in context like climate change. There's some urgency to find new materials, for example, for certain applications. So we can improve this with generative models. And the way to do that is essentially help in the hypothesis generation, in the generation of candidates. And this can be, useful or it can be useful because generative models can learn from data, can generalize to and explore regions of the search space, and potentially build better queries than a human with large but limited expertise can do. So that's the idea, to have this kind of active learning in the sense that we repeat this multiple times. We repeat this multiple times in the space of an experiment and generate new candidates. Are you seeing the slides change, by the way? Amir? Hello? No. Okay.
So I think he can hear us, but no, yes, that was what I gonna ask. We cannot see the slide change.
We're on slide 1 still.
Yeah, I thought that's a long introduction, but
yeah, I just noticed that because I have like a duplicated thing. I've just noticed. So then it all must have been a little bit awkward. Let me see. I'm gonna do this again. That's not what I wanted. So people were like, okay, what is this guy talking about?
I said, yeah, this is one hell of an intro.
Wow. Okay, now it works, right?
Yeah, slide 2 is what we see. Yeah.
Well, you definitely had time to to scan the QR code then.
Yeah, I mean, I
All right.
shared the link in the chat. I did do that. So
Yeah. But it's like, okay, I was talking about this at the beginning, as for kind of summary of my research, and then this was the outline I talked about, and
and
I was
how many
showing this
tens of
slide. So very quickly to not lose more time, but I was talking about this kind of loop in the traditional discovery cycle and how we can introduce a machine learning model to learn from data, but that's not enough. So we can have a generative model to improve this even further. And this is where I was. Apologies for yeah, for this problem. So hopefully it still makes some sense despite not having seen the slides in while I was talking. Again, you can go back to that, but the idea was just to introduce this. So I will continue. And by the way, if there's questions about clarification, please, yeah, ask them. I think that would be better to clarify things that stay with the doubt or with the question. So I want to briefly mention some challenges of this, and I will do it with an example that is hopefully intuitive. So I imagine I give you this problem. We have this Tetris board, very small, and this set of 5 pieces that you can put in the board, following the rules of Tetris, that the pieces will fall to the bottom. And I imagine I tell you, okay, give me a solution that minimizes the empty space in the board. And this is trivial. Very quickly, you can give me one answer. For example, this one. Let's imagine the score is the number of cells that are occupied by the pieces. Okay, very trivial, very simple. We can make it a little bit harder if I tell you, okay, it's not enough to have just one. I want all of them or many of them. Then this is still pretty easy. It will take you a few seconds, but with a little bit of time, you will be able to figure out all the solutions to this problem. But how about this? We make this much more difficult by having a bigger board and a much larger set of pieces. Again, you can find very easily one of the solutions. For example, one of these. This is because it's still intuitive. But now imagine I tell you, well, actually, we're now not anymore minimizing the empty space. Now we're doing something else, and we don't know exactly how to formulate it, like mathematically or formally. So we are, in this case, optimizing an unknown function. For example, I could tell you these are the examples, the potential arrangements of the three spaces here that maximize our unknown function. Then this becomes a very hard problem, actually, right? Especially if the evaluation of this function, so kind of verifying the score of a solution is expensive, as you can imagine. And I want to make the point that materials and drug discovery involve finding candidates with rare properties, meaning there's very few solutions to our, or very few candidates with the desirable properties compared to the amount of candidates that exist, which can be combinatorially or infinitely many. And yeah, the point I want to make is that it resembles a lot this kind of problem I've illustrated with this kind of silly intuitive example with the Tetris pieces on the board. Okay, for example, it is the case with the design of DNA sequences. This actually conceptually is much simpler than the Tetris example I've just shown, because DNA can be formulated or can be represented as a string, and there's no like a sequence. There's no multiple places where you can attach the nucleotides. It could be similar to the design of small molecules for drugs. it can be formulated in a similar way, and we also face these kind of challenges with a combinatorially large search space, with the molecules with the desirable properties are rare, etc., etc. So it's similar problems, and of course, it's the case as well with crystal structure generation, which we will get into more detail in the in the remaining part of the tutorial. So to summarize the challenges of material discovery, drug discovery as well, we are dealing with very large, high-dimensional search spaces. This is a problem. This is hard. So we need machine learning methods, if we want to apply them for this problem, that are efficient and have good generalization capabilities. Another challenge is the underspecification of the objective function. I haven't talked about this yet, and it's a little bit, maybe less intuitive, but typically we care about many things when we want to discover new materials, new drugs. And of course, there's going to be like a key property that we need to have in the material, but that's typically not enough. We also need that the material is easy to manufacture, is cheap, is stable. There might be other properties that it needs, etc., etc. So just optimizing one single property is not enough. And one way to deal with this is coming up with diverse candidates. So diverse solutions with the goal that at least one of these set of diverse candidates down the line, when we check these other properties, other requirements from the candidates, at least one of them or a few of them satisfy them. Right? So there's this need for diversity. And the point here is that many of the methods that exist in the machine learning literature, right, like reinforcement learning, have a harder time with diversity. Right, they are very good at optimization, but they tend to lack diversity. And it's similar with more kind of established traditional techniques like Markov chain Monte Carlo for sampling. It's good at diversity, but then it struggles to to find many modes of the underlying distribution when you move to high dimensions and discrete, for example, discrete search spaces, or hybrid, discrete and continuous. So we actually need to combine all of these things, and that's why GFlowNets, generative flow networks, were introduced, which is the topic of this tutorial. And in the coming slides, I'm going to try to give you a gentle and relatively brief introduction to this method. But I want to take a moment to check if there are questions about this first part. Okay, if not, I'll move on. But again, feel free to interrupt me. So I want to start by giving you what, in my opinion, are the three key ingredients of GFlowNets, especially in their application for the sciences, for scientific discoveries in particular. Remember that the goal here is to sample from unknown distributions in discrete or mixed high-dimensional spaces that are very, very large. So one of the key ingredients is diversity. Diversity is kind of baked in as an objective of the method, as opposed to reinforcement learning or like typical versions of reinforcement learning. And the way to do this is that we typically have a reward function. Let's call it R of X. X is a candidate. And what GFlowNets do is to sample proportionally to the reward. And this gives us diversity immediately. We'll get into the details in a moment. Another ingredient is compositionality in the sample generation. This means, or the way this is done in GFlowNets, is that objects, a material, a crystal, a molecule, a DNA sequence, is generated sequentially by applying actions multiple times, doing multiple steps, and this yields structure and potential for generalization in a machine learning model. So the composition yields generalizable patterns. Finally, the third ingredient is that deep learning is used to learn behind the scenes the generation and the sequential generation of these objects X. In particular, what we can learn with deep learning is a value function that models the transitions between different states, between different parts of the decomposition of the objects. And this, the combination of compositionality and deep learning gives us the potential for generalization from these patterns. All right, so I'm going to delve a little bit deeper into each of these ingredients now. So now, again, let's assume we're given an objective function R of X. This can be a property of a material, of a drug, whatever. So R of X, just a score of how good a candidate X is for our purposes. So then we can see GFlowNets as a generative model that is specifically trained to sample objects X from a space, calligraphic X here, according to a sampling policy. So they're going to learn a generation sampling policy that is going to be proportional to the reward function. So essentially this, we learn a pi of X. This is our policy, or like the probability of generating X is equal to R of X, the reward, divided by a partition function Z that is essentially the sum of all the rewards in all the space. If X is continuous, by the way, this would be the integral, obviously. And of course, if we have a very small space like the Tetris, the mini Tetris example I showed at the beginning, we can compute Z, because it's just the sum of all the rewards of all these arrangements of pieces, right? But in general, it's unfeasible to compute Z. But that's okay, because all we care is we don't need to know X. We need to sample proportionally to R of X. Okay, so it's going to be enough. And I don't know if this is clear, but this is very important. So if it's not clear, please let me know, and I'll try to explain it in a different way. But the idea is that if we sample proportionally to the reward, imagine the reward has this shape in a two-dimensional space. So there's like 4 regions of high reward in the corners of this two-dimensional space. If we are able to sample proportionally to this reward, then it means we're going to sample diversity. We're going to sample diverse candidates. So we're going to be able to sample from the 4 corners of high rewards. Okay, does that make sense? All right. So that's about diversity. A few words about compositionality, and I want to mention that the idea of compositionality is fundamental in a lot of areas of knowledge, like semantics, linguistics, mathematical logic, and yeah, people argue that it's a cornerstone of human reasoning. The idea of decompose complex thoughts, ideas, complex objects into parts, right? So this is very useful. In the case of the Tetris example that I was using, if you think about it, there is a meaningful way of decomposing these objects. I'm talking about this. This would be like our objects X. There is an obvious way to decompose that into parts, into the arrangements that we build by adding piece by piece. So imagine we start with the empty board. We can add the yellow square piece that takes us here. We can add another one. It takes us here. We can add another one. Takes us to the full board. And here we can add more pieces. So we stop and we get our reward, 12. So this is a decomposition of objects. Objects like with 3 yellow squares into parts. And of course, there's different paths we can follow in this tree. So from here we could from this state, the partially constructed object, we can add the blue piece and get here, and so on and so forth. Get the reward, and this, we can build other parts of the tree, And you can imagine, this is a small example, but still yields a pretty big tree. In more general cases, this is not a tree, but a graph, a pointed graph actually, that kind of represents the decomposition of our objects. And we have a key here is that we have the flexibility to design this decomposition the way we like. But this is going to be very useful, and hopefully will make sense when we talk about the crystal GFlowNet in particular. So it's a conclusion of this idea of compositionality, that the composition of sampling processes into meaningful, that's a key here. This is not like arbitrary decomposition. The decomposition into meaningful steps yields patterns that can be picked up by a machine learning model, right? And help us with the generalization. All right, I'll skip a little bit to say a few words about the deep learning policy. So again, I'll use the Tetris example. Imagine we have this slightly larger board. So now it's not a tree anymore because there are multiple states that can take us to this state ST, and also from ST there is different actions we can take. So this would be the case for this specific example. And then the way GFlowNets work is that you're going to learn a value function f to model the transitions. So what is the worth? What is the value? What is the probability? There's different ways of interpreting this. We call it f because of we can see this as a flow. That's hence the name generic flow networks. So we can quantify the value of applying an action with this function f, which is learned by a neural network with parameters theta. Okay, and that's the idea. There's going to be a deep learning model behind the scenes learning the value of these transitions. And there is a theorem in the original paper that introduced GFlowNets back in 2021 that tells us that if the sum of the flows into state S, so the sum of this flow and this flow, is equal to the sum of the flows coming out of state S, so the sum of this and that, then we will sample proportionally to the reward. And this, of course, this has to apply for all states. All right. So theoretically, if we are able to train a model to achieve that, then we will be able to sample proportionally to the reward, which is what we want. So that's very good news. All right, this I'll go through very quickly. Leave it here.
Alex, there is a question in, does compositionality implies that the input space has to be discrete and known beforehand, like knowing the list of molecular fragments? I think this question is for the previous parts still.
The decomposition, if we're talking about this,
yes,
the decomposition is something we have the freedom and flexibility to design ourselves. So, for example, if we go to, I mean, this is an example for the Tetris, but if I go back to the slide with the DNA sequences, which is very simple, it makes all the sense to generate DNA sequences as adding one letter, one nucleotide at a time, nucleobase at a time. So we could start from an empty sequence, and then GFlowNet will decide, okay, now G, now A, now G, etc. But this is just one of the options that is available to us. We could choose to add, groups of 4 letters at a time. Why not? So this is kind of one of the nice properties of this framework, that it gives us the freedom to design how we want to do this generation. In the case of small molecules, it could be fragments of molecules, or it can be tokens in Smiles representation, which is kind of equivalent. But it could also be putting atoms in the 3D space, right? Or it could be constructing the molecule by setting the bond lengths, bond angles, and torsion angles. So there's really a lot of freedom to do this, and it will become clear as well how we made some choices in the case of Crystal GFlowNet. Does that answer the question?
I hope so. Luis asked it in the chat, so
Okay, I'll
Yeah.
take that as a yes. If not, please ask again. I
No
hear no
problem.
feedback. So, right. So I was talking that there's some extensions that I'm gonna go very quickly through that. I just leave it here for reference for you. But we extended this to multi-objective, so we can have multiple rewards at the same time. Of course, initially it was discrete spaces, but we extended it to continuous spaces, and of course hybrid. This is going to be clear when we talk about crystal GFlowNets. We've used it for molecular generation. Here the generation is on the space of torsion angle, so we make increments to the torsion angles of a given molecule to sample from the Boltzmann distribution. We've used it, in fact, for biological sequence design, not only DNA, but also proteins and molecules represented as SMILE sequences. And perhaps for those who are interested to read more about the general framework for scientific discoveries, I would recommend this review paper, GFlowNets for AI-driven scientific discovery, which tries to kind of give a full overview of what I'm talking about, in fact. And there is code that we're gonna see later. I leave the link here for reference to the repository. And yeah, this takes me to the last part of the, let's say, the theory part of the tutorial, which is about the specifics of crystal GFlowNet. So I imagine many of you are already coming from materials from a materials background, material science or physics, chemistry. But just in case there are people without this background, what are crystals? Essentially, crystals are solids that have a lot of structure in the ways the atoms are arranged. So there's like symmetries that govern the arrangements of the parts of the material of the crystal. So that's the main thing, and this is opposed to amorphous materials or polycrystalline that kind of mix the two, right? There's parts of symmetry and parts that are more disordered. Here we are concerned with inorganic crystals for now, just to make sure. There's of course organic crystals. Here we're going to talk about inorganic crystals whose constituents are atoms or ions. And an important aspect of crystals is that we can characterize the structure of them by the unit cell, which is the smallest imaginary box kind of containing the atoms in a specific spatial arrangement with certain symmetry. And then this unit cell is going to repeat in all directions. Well, it depends on the structure, but in general, let's say in all directions in 3D space, creating this mesh of parts that are connected to each other, providing some symmetry to the whole structure. I apologize for my, I'm not a material scientist. I work on this, but I know it's not like a super formal description, but just for everyone to be on the same page. And why do we care about this? Well, crystalline structures are key components of things like electrocatalysts for fuel cells, for hydrogen storage. They are involved in a lot of industrial chemical reactions that are responsible for a lot of carbon emissions. So there's a potential here to discover electrocatalysts that are more efficient and require less energy, also for carbon capture. And solid crystals are also used or could be used for new batteries that are safer and more efficient. They are also used in photovoltaics for film materials, etc., etc. To me, this is important because there's different applications that can have an impact on sustainability, which I care about. But it's challenging. It's difficult for the reasons we have discussed, right? I won't get into this again. So how did we tackle this problem of crystal structure generation using this GFlowNet? So again, we could optimize atomic positions directly, but we thought that instead of doing that, that would be like the kind of more machine learning direct way of doing it, we try to draw inspiration from theoretical crystallography to figure out more meaningful ways of generating crystals, to introduce inductive biases, to introduce information into the problem. For example, as many of you will know, there's it is possible to decompose crystals, or the representation, the description of a crystal, into the space group, which tells us about the symmetry operations that the specific symmetry allows. There are 17 symmetry groups in 2 dimensions, 213 3 dimensions. So this is a discrete finite property. There is also something called the lattice system. There are 7 lattices, cubic, hexagonal, orthorhombic, rhombohedral, etc., triclinic. And these are described, the lattices are described by the lattice parameters, A, B, C, alpha, beta, gamma, and there is relationships between them, as you can see here in some cases. Take this one, all the angles are the same, alpha equals beta equals gamma, etc., There's like relationship between these parameters that, again, can be leveraged to better train machine learning models. And if you remember what we did with the Tetris, the small Tetris example, we could do something similar with our crystal GFlowNet, and that's what I will try to explain in this slide. So imagine we want to construct a crystal sequentially, step by step. And again, this is just one. What I'm about to explain is just one of the possibilities we have. We could do it differently, and this actually, if there are people interested in this problem, and by the way, if that's the case, get in touch, because we're looking for students and collaborators to work on this. But you could envision other ways. That's possible, and I'm going to explain one. The way we did it is to start the generation of a crystal with a space group. And we, in turn, decompose the generation of a space group into 3 parts, which is like the selection of a crystal lattice system, a point symmetry, or 5-point symmetries, intosymmetric, polar, enantiomorphic, etc., and then the space group itself. There's a hierarchical relationship between these properties. Fortunately, I don't have time to get into all the details, but that's the idea, that there's a hierarchy governing these relationships. And once we have the space group, imagine the space group is 225, which is a cubic lattice. We get into the generation of the actual composition. So which elements or how many atoms of each element. And that's exactly how we do it. The GFlowNet selects the space group and then can do something like, okay, let's get 4 oxygens and then 8 lithiums, atoms of lithium, of course, and then we stop. That's it. But it could have, in different trajectories, it can make different choices. And something important is that because we have flexibility to design this ourselves, we can introduce constraints. So, for example, there are constraints governing the properties of the space group, like I said. So you cannot select a cubic crystal lattice system and then space group that is hexagonal. In the same way, the amount of elements and atoms has to satisfy the constraints imposed by the space group, and so on and so forth. Here, C3, this is we also impose constraints on the charge of the system. It has to be neutral, things like that. So this framework allows us to introduce these hard constraints that are very difficult to introduce with other generative models. And finally, once we have the space group and the composition, we select the lattice parameters, and again, we introduce constraints from the space group. So again, if we have a cubic lattice, then we only have to select A, because B equals A, C equals A, and alpha, beta, gamma are all 90 degrees. So we cannot just mess up with this. There's our hard constraints. That's a very nice property to have. And so at the end of this trajectory, we have this output which is a representation of a crystal by the lattice parameters, composition, and space group. Of course, there's more things we could have about this crystal, like specific atomic positions, Wyckoff positions, and whatnot. But at this version of the crystal GFlowNet, that's what we have, and we can compute, we can calculate the reward for this X for this specific output, right? And we could have a proxy model for the reward. Imagine it could be the formation energy, but because the formation energy, if we want to compute it with DFT, it would be expensive. We can use proxy models that are cheaper than that. That's what we do. This has a number of advantages. One is the possibility of include the constraints, like I have mentioned, and that we do the search in a lower dimensional space than if we did this in the space of atomic positions of like all the 3 coordinates of each atom. That would be kind of overkill. This is what other methods do, and it's possible, but it's much more inefficient. And again, this allows us to generate materials more flexibly because we can use the same model for different properties. Yeah, it works the same way. There's nothing to change. And once we have the model, we can also impose constraints at the generation. We can say, okay, now I want to generate only crystals with lithium, for example, for solid electrolytes for batteries that are like lithium batteries. This is also possible with this framework, and I will show an example in a moment. So, okay, I should be finishing this part soon. So kind of quickly, I'm going to show you the kind of results you get with this method. We did experiments with formation energy as a property, as well with the electronic band gap and the density. I have in the slides here the results for formation energy and band gap. So maybe I'll focus on formation energy. Imagine we take, well, you don't have to imagine, I mean, you can imagine, but that's what we did, in fact. Take the materials project dataset. We call that our validation set. It's also a training set, but of course it's divided. We can plot the distribution of the formation energy. And this is something that has to be low, like smaller than 0. This is the case for the majority of crystals in the materials project because there's a bias towards stable materials. But yeah, the idea for those who are not familiar is that the lower the formation energy, the higher the chance for the material to be stable. Of course, the idea of stability is a bit more complex than just this, but in general, we can say that it's a good thing to have low formation energy. If we take a crystal GFlowNet, as I explained it before, and we let it generate crystals before we train it, so kind of at random initialization, the distribution we get is this one here on pink. So it's a distribution that is mostly on the positive part of the formation energy. So this is bad, let's say. This is not good because the majority of the generated crystals are going to be unstable. But once we train the crystal GFlowNet, we get a distribution that has even lower formation energy than the validation set. So that's good news. It means that it has learned to generate crystals with low predicted formation energy, predicted by the proxy model that we use. So yeah, that's good news. We did very quickly something similar for the band gap, except that here we don't want the lower the better. We wanted to have values close to a target band gap of 1.34 EVs. Again, this is the validation set. This is random distribution, and this is a distribution we get after training. So again, good news because we get a distribution kind of centered around the target value. So this is essentially showing that it is doing what we want it to do. And in terms of diversity, which I've been arguing that that's very important, I think I'll show this and then stop. Is there a question?
Yeah, I have a question. So the predicted band gap value, that was done with like a typical DFT method, or yet another machine learning neural net to predict the band gap, or?
It's a good question. This is going to become clear in the tutorial part, but we write predicted because it's a model.
Okay. Okay.
So both formation energy and electronic band gap is predicted via a pre-trained machine learning model. So we train it from data, and then we use it to train our model, because using directly DFT would be too expensive to train a GFlowNet.
Okay, so it's the whole vertical integration. I see. Yeah.
Yeah. So I won't go back to the beginning of
Alex,
the slide.
there is another question. Sorry, in the chat before you continue. I think Eric is asking about the composition. Does the composition in the last slide, I think it's the slide where you were discussing the Bravo lattices, or I don't know, fully determine the lattice angles, or there is still some freedom the model has to determine?
I'm not sure I understand if the composition determines the lattice angles. No, the lattice angles need to be kind of selected, sampled by the GFlowNet. If the question is whether this representation, this generation, fully determines a crystal, the answer is not always, because there will be freedom for the atoms to sit. In some cases it is fully determined, but in general it is not. So this is like we can see this as a first step towards having like full description of crystals. And I can say that we're currently working on all that, and we're pretty much done, but the results are not published yet, so that's why I'm not showing it. But this is like a first version where the crystals are not fully determined. But yeah, it's essentially possible and feasible to do it. So you can imagine that you would extend here on the right, having more modules that will determine the atomic positions in the case there is flexibility for that. All right, so yeah, essentially, I won't go into the details of this, but our analysis of 10,000 samples generated by the Crystal GFlowNet, and by the way, generating samples is very efficient. This takes like a few seconds. Our analysis is that there's a lot of diversity in the generated samples, and that's again good news. This is a general property of GFlowNets for any application. Diversity, like I said, is kind of baked in the method. I don't know if it's, I think I'm going to skip this. I leave it for you to explore. So I will conclude saying that again, the problem of generating crystals with desirable properties is pretty hard. There's a lot of methods in the literature that kind of struggle with this preservation of symmetry, and we try to incorporate this as hard constraints into this model that we call Crystal GFlowNet, and that our results of this first attempt, this first method, is that the generated samples are diverse, they have high scores as shown in the plots, and have the desired constraints because they are hard constraints incorporated into the model. And this can be flexibly extended. In fact, like I have just said, we have been doing this in the past months, and yeah, I think that with that it will be the time for some hands-on tutorial. If that sounds good to you. So I have prepared this collab. I don't know if that's big enough.
Could you share that the link in the chat?
Yeah, I'm gonna do that. It's also in the slides for those who got it. Well, I hope it works. Let me know if everybody can access it.
Looks good on my screen.
It's good. Okay, perfect. Then I'm just gonna get started.
So Alex, before you start, there's another question in the chat.
Sure.
I was wondering whether model improved the values of formation energy or band gap by changing the atomic positions, which means gave new crystal structures. Or you can read it yourself.
Yeah. Okay. So hopefully this will become clear with the tutorial. But I'll say now again with words what's going on here. Maybe I will go back to this slide for that. So I'm going to repeat this because I think it's very important to understand in general how GFlowNets work. They're a bit different than two other models. So, but the idea here is that we have a generator, we have some machinery, let's say, an algorithm that is able to generate things from scratch. Okay, if the things that we generate are, or the way we generate these things, in this case crystal structures, are kind of like arbitrary, this is pretty useless. The key here is that we have an algorithm that learns to generate crystals proportionally to a reward. In this case, proportionally to the, if we're talking about formation energy, the reward is the exponential of minus the predicted formation energy by a model. The details don't really matter. The thing is that it learns to sample crystals that with a probability proportional to the formation energy, right? This formation energy, ideally, we would take it from running DFT, but this is not feasible because we need to query, we need to compute the formation energy, estimate the formation energy many times as we train the crystal GFlowNet. But instead, we can take materials project data, train a model to predict the formation energy, and then use this predictor with as our reward function. We call it proxy. And maybe you're wondering, okay, but this predictive model is going to be bad. And actually, I don't have the number here, but anyway, I know it. I think I remember it by heart, which is the mean absolute error of the predictive model trained to predict the formation energy is 0.12 EVs. Okay, so it's pretty low. It's not perfect, but it means that yeah, the predictions are going to be very similar to what DFT would give you. So essentially, we can use it, and of course, if you want to use this generated materials crystals for something, then you would have to verify like with DFT, but you would do that for the best candidates only, or the things that are most interesting to you depending on your application, not for like thousands of crystals. Hopefully that makes more sense now. And yeah, so let's get to the tutorial. So like I said, there is a repository. This is the repository here. You can take a look later at your own pace. What we're going to do here is to essentially clone it and install the dependency so that we can use it here on this Colab notebook. But I will mention that there is a README here that gives more background on GFlowNets and has like some instructions about how to install it step by step and so on. So hopefully that you can take a look later if you want to do it outside this Jupyter notebook as well. So I will just run this this cell, which is going to do these steps, essentially cloning the repository and installing the dependencies. It's going to take a few seconds. So in the meantime, I'm going to try to give you an overview of what we're going to do. We're going to start with a more intuitive like version of the GFlowNets, which is like generating like say words as in the Scrabble. Imagine we're playing Scrabble and we want our GFlowNet to generate like sequences of letters. By the way, in the slides, you have a few, I'm not going to go through that in the interest of time, but at the very end of the presentation, there's a few slides describing this idea of the Scrabble, okay? I'm just going to do that so that we have a first approach to this that is less complex than the crystal. So in this case, we're literally having a GFlowNet generate one letter at a time until we reach a maximum of 7, or it can stop earlier, maximum 7 letters. Okay, it's still working on it. I guess you will be doing the same on your machines. So yeah, we will see how to train this Scrabble task, for example, in one like command that you would do in a terminal, or you can also do it here in the Jupyter Notebook. We'll see some results of that very quickly, and then we'll move to a Crystal GFlowNet and see more details of the method. In the meantime, well, I think it's going to take like maybe 30 more seconds or so. If there's any other questions, yeah, it could be a good time. I see some errors here, but I think it shouldn't matter. Okay, I think it's done. So, like I was saying.
Oh, Alex, sorry. There's a question in the chat, so I think it's better for you to read it yourself.
Yeah.
Or I can read it for you.
For small molecules, if I have a scaffold and want to attach fragments to generate a molecule with desired properties, do I need to have a list of fragments beforehand? Yes. Yeah. You would. That's something you can do. You have other options, but you would have to define, okay, what are the fragments I can attach to my molecule as I build fragment by fragment. You define that, and you have to code it. There is a tutorial. If you're interested in doing that, there's a tutorial I gave, and it's recorded about how to actually code your own environment, your own task. It's not too hard. Depends on how complex you want to make it. But yeah, that's what you would have to do. And then will it generate fragments like diffusion just from nothing? No, it's not like diffusion, which is like adding noise. Kind of, it adds diffusion models add noise to existing data points and learn to do the diffusion process. GFlowNets, as a matter of fact, there's a way to connect diffusion models and GFlowNets, but more intuitively, what they do is not to denoise. They build from scratch. They build something from scratch. So if we take the Scrabble example, we start from nothing, an empty sequence, and we're going to add one letter at a time. If it's molecules, maybe one fragment at a time. If it's a crystal, we do it with this more complex thing of space group, composition, lattice parameters, and so on. But we build from scratch. Okay, so if you successfully install the GFlowNet package, then essentially you just can use like Python to run the train.py script, and you specify properties using Hydra configuration. So this is one way to run it, and we're going to see how to run it like kind of more manually on specifying everything on the terminal. But you could do something like this. You specify the environment, you say Scrabble, the proxy is also Scrabble, and you could just run this. Now it's initializing, it's telling us where it's storing the logs of this run, which we could see like here in this log, directory. Maybe I'll close this and open it when needed. And now it's training. And you see in this case, it trains pretty fast. This is showing us the number of iterations. This is training for a maximum of 5,000. This is a pretty simple, quick example. So it trains very fast, but of course, it's not going to learn as much as it would learn if we train it with a slightly bigger model with a little bit more of refined hyperparameters. This is just for illustration purposes, but we're going to see that even by training this Scrabble GFlowNet for about a minute or two, is already going to start showing like visible improvements with respect to random generation. And while this finishes training, takes still like 2000 iterations, like 40 seconds, I would like you to think about the complexity of this task. Okay, so hopefully many of you have played Scrabble. You have to come up with words. Each letter has a number of points. Then the score of the word is the sum of the points. And this GFlowNet is trying to learn to sample words with high scores, like out of thin air, kind of. There is a reward function that every time it generates a sequence, it tells the GFlowNet the reward. And then when it needs to learn is to go from sampling random sequences to sampling sequences with high scores. This is actually a hard task because the search space is huge. It's like 20 something letters to the power of 7. That's pretty big. Plus 20 something to the power of 6. So this is just an approximation. All right, it's finished training. Now we can do Python eval.py. This is to evaluate and sample from the trained GFlowNet. I have to adjust the path here. So I'm going to copy paste the new path, and I'm going to tell it I want 1,000 sequences. I just run this. It is initializing the stuff it needs, telling us some configuration, metrics, and that's it. It already generated 1,000 samples. And now we're going to do a quick visualization of this. So what happened here? Okay, the usual problems live. I don't know what this. I hope it's installed already. Nope.
I think it's a pandas or numpy issue.
Yeah, but like, of course, I didn't get this. I run this many times and I haven't got it. Oh my god. Is it with pandas actually? If I comment pandas. Okay, I'm gonna try to guess very quickly. What is the? Is it if anybody has run this on their own Colab? Can you tell me if you get the same issue? Because I've run this multiple times before.
No, I got it to. I had it already ahead of you, and I thought it was maybe just my fluke, but no. I tried upgrading numpy. That's what the AI said to do, but
okay, let's try, because otherwise. I wonder if it's the version. The one issue is that NumPy 2.x is not compatible with some versions of PyTorch, so I wonder if that's the issue. But yeah, of course, this is not working now, so we need to go back here and run this. Oh my god, why is this? I wonder if it's related to these errors we saw before. God. Well, apologies for this. I'm trying to figure out something quickly, but oh god, this is really well. Yeah, but this is what we had before. I believe. No, same problem. Well, let's, yeah, apologize. I'll try to fix it later, but otherwise we're gonna be debugging here. So I think I still have the outputs here. So hopefully I can just show it. So what I was doing essentially is reading the generated samples. Show hidden output. Yeah, of course I fucked this up. But yeah, I was plotting what the cells are doing is plotting the distributions of the scores. It says energies here. Imagine it's just the scores of the Scrabble, and this is what they look like. Of course, if we just see this by itself, there's not much we can tell. Is this good? Is this bad? So what I did after, what this cell does, it's similar to the previous one. We would have to change the path as well, but I'm not going to do it in case it fails. And we're adding here random minute true. So this is going to generate 1,000 samples, Scrabble words, but at random. Instead of from the different, it's going to do it at random. And then we can plot it again. This is what it would do. This would be the data frame that we built. And if we plot it, it looks like this. And then what I'm doing in this cell is merging the two data frames, the one with samples from the GFlowNet and the one with samples from a random distribution, so that we can plot them together. And this is what it looks like. In orange, we see the distribution of scores from the random distribution. And in blue, we see the distribution of scores from the GFlowNet samples. It's only a small improvement, but we already see that it has improved. And again, I want to highlight that this trained for 1 minute. If we train for longer with better hyperparameters and so on, it improves a lot more. And it starts generating sequences with very high scores. There's some version, if we are curious about this Scrabble kind of toy thing, there is an option to make it check with a vocabulary if the words exist, so you can force it to, or encourage it to learn words that exist actually in a dictionary, and it completes it learns the task successfully. Okay, so with that, we can move to the Crystal GFlowNet. Specifically, I cross my fingers so this works. Jesus Christ, the same problem. You might need to downgrade the Pandas version and keep it to. But what is? Like, I swear to God, I did that this morning, and it worked. And yesterday many times, so I don't understand. Python freeze grep numpy. I'm going to install this doesn't work like this. This is very strange error.
You want to explain to us the pseudocode, I guess?
Yeah, I'm wondering. I don't think I will be able to solve it like right now. So maybe let's. I will just show the code. It's well, actually, I'll show the code and then I'm gonna show you live when on the terminal where it works. Jupyter notebooks are a bit. Yeah, I actually don't use them often, but yeah, let's find an alternative for the 15 minutes. We have 15 minutes left, right? Kind of.
Yeah,
Perfect. So don't worry, I'm gonna be able to show pretty much the same, and I'll try to figure this out later and fix it so that you can play with the notebook. So before with the Scrabble here, I was showing you the command you would run to train a model just from terminal using the configuration files. You can take a look at the description in the README where we explain this. But this is kind of like a straightforward way of running a GFlowNet. If I added here the details in case you're curious of what's going on behind the scenes. And what happens, so here first we would import all the different components that we need. And here we are kind of initializing a GFlowNet to be able to train it and to do other things with it. So one thing we do is, okay, I see now that this is actually an outdated version. So probably it got lost with me saving it, and that's why. Okay, I'll fix it. But here we initialize a crystal, and we also initialize the proxy. Yeah, in this case, this is the outdated part. We could use a different proxy. We also need to initialize the policy models for the yeah. There's two policy models. One is for learning backward trajectories. The other one is for learning backward. Forward and then backward trajectories. And there's another a number of other components that help GFlowNet kind of handle different things. I don't think it's worth getting into all the details, but there's something that's called the buffer, which handles like data set and a replay buffer. There is a logger that helps like plotting results to 1 dB, for example. There's an evaluator to compute metrics as you train. And then there is finally the most important component, which is the GFlowNet agent, which is the thing that brings everything, is the module, the class that brings everything together. So you pass it the environment, the proxy, the policies, the buffer, the logger, evaluator, etc. And then this allows you to set more characteristics, more properties, hyperparameters of how you want to train. Of course, there's a bunch of things. In general, we don't need to tweak all these things one by one. There's some configuration files that let you kind of set some hyperparameters that work pretty well in general, and only if you want to adjust something for your needs, you would play with this. Oh my God, there's a lot of stuff that got deleted, so I'll have to do it again. So what I was going to show you is the following. I'm going to show you this other notebook that I did kind of on the side to prepare for that. So for the Crystal GFlowNet, as I was saying, you can train with a model of your property, like a crystal, like the formation energy that you train, or any other property. For example, we have the band gap. You could train your own model of your property of interest, and train a GFlowNet to optimize for that property. And what I had prepared for the session is like a synthetic proxy, a synthetic reward that we can actually visualize here on the notebook. And it's synthetic in the sense that I have, for the purposes of illustration, I have reduced the space of crystals that the GFlowNet can generate to only two space groups, which are 225 and 229, and two elements that are palladium and platinum. This, we could, in general, in the GFlowNet paper, in the crystal GFlowNet paper, sorry, we have many more space groups, many more elements, but it allows us to constrain our problem to just these options. And I do it only for the purpose of illustration here, so that we can plot things nicely. All right, so this is effectively palladium 4, palladium 2, platinum 4, platinum 2. And these are cubic lattices, so there's only one parameter, A, that GFlowNet has to select. So we can visualize things in just one plot. And I created this synthetic reward, again, for visualization purposes. And it looks like this. So the reward is on the lattice parameter A, which here, by the way, it's just normalized from 0 to 1. In angstroms, it would be from 2 angstroms to 4 angstroms. I should have adjusted this. But essentially, I make it look like this, such that it has two modes, so two regions of high reward on different parts of the lattice parameters, with kind of like a valley of low reward. Imagine this is the formation energy, and the specific height and locations of the reward changes for the different combinations of space group and composition that you can have. But there is symmetries here, so it tries to simulate kind of what would happen in general, that there is structure that can be learned and generalized by a GFlowNet. So yeah, this is what it looks. This is the true reward. And when we train a GFlowNet to learn this problem, it learns the following. Looks like that. So this is like a histogram, and this is the kind of density estimated for this problem. It's not perfect, but you can see that it's quite it's quite close to the true reward. This is I don't know if this is clear, but this is the distribution of rewards from 10,000 samples generated by a already trained GFlowNet. Okay, and it is learning that on this location of the lattice parameters, and on this location there is high rewards for the different combinations of space groups and elements. And again, it's not perfect, but it's pretty close to what we want. So again, this is like a toy version. In the notebook that I had prepared, it shows the way to train it, and yeah, it kind of trains relatively fast. So yeah, because it's a small problem. But if you wanted to train the crystal GFlowNet with a model of the formation energy, for example, it takes about it depends on how much you want to train, but in like 4 or 5 hours, it's already generating very good samples. And for comparison, like this, many of these diffusion models that are also being used in the literature for this kind of problem, in some cases it takes like literally like weeks to train. So it's one of the features.
And you ran it on CPUs, I think you said?
Typically? Yeah, CPU only machine. Actually, I can show you just, this is kind of like research in progress, but I don't mind. Let's show this one. This is a recent model I've just trained. And actually, I will delete this. I will show first the time that I'm talking about. So we This is y-axis is the number of iterations. 100,000 iterations is far more than we need, but in 400 minutes. Okay, and now we're gonna see the rewards. Actually, I'm gonna show the scores because it's the formation energy itself. So this is y-axis is the formation energy as predicted by the model. We can see that as we train very quickly, it's already going to minus 2 point high. And this is actually, it would be tricky to explain, but it's not as low as it would get, as it would be at sampling time, because here there is some replay buffer going on and some random actions that make it higher and so on. But you can see that very quickly, it starts sampling crystals with very low reward. And then we train it for longer just to let it explore more and more and more. But very quickly, this would be minutes, it's sampling, good crystals. Good crystals meaning low formation energy.
So I think we have one more question here.
Yeah.
I think it's back to you were showing originally with the bimodal distributions in Gaul. The person asked, each point on a density versus a plot is a crystal with different composition.
Sorry.
In your other tab there, Gaul.
Here. Each point on density versus a plot is a crystal with different composition. It's a bit more complex than that, but kind of. It's each point. It's each crystal is a point, so crystal with different space group, different element. In this case, the composition is just one element for simplicity, platinum or palladium, and then a value of the lattice parameter A of the side of the cube, right? And depending on the choice of A, of the lattice parameter A, you would get more or less reward. And you can imagine that if you do this at random, then you would generate a lot of crystals in this region as well, which would have low reward. And here we are simulating a situation where we are not interested in those. Those are not stable. We want to sample mostly over here with these values of A and these values of A. Does that answer the question?
I think so, yeah.
Okay. Right, so we're kind of at time.
Yeah, I'll ask one question. So,
Yeah.
when you define like for GFlowNets, right? It seems like you're defining the composition. So, you're bringing in a lot of your own domain knowledge. There's like human intervention, and I don't know. It seems like that helps improve the quality of what's outputted. I don't know from your experience if you've compared it to those generative models. Sometimes there's things that are really just hallucinations almost.
Yeah. So what's the question?
Well, it's more of a comment. Just GFlowNets is there's like human like domain knowledge that's injected, right? When you state
Right.
and define the boundaries of the composition, right? And I don't know in generative models, I don't know if they do have that ability, but
yeah, I mean, that's true, and I don't want to kind of claim that it's perfect already or anything. It's far from perfect, and there's a lot of improvements that can be done. There's also a lot of improvements going on in the literature. There's more and more work on generative models for crystal structure generation, and they're getting better at preserving symmetries and so on. I work specifically with GFlowNets, and I think what I can say is that one of the nice properties, or the kind of the summary of the nice properties of GFlowNets I see is flexibility. I've mentioned it several times, but I think it's important. There's flexibility on different aspects. Is that you can really adjust it to your needs. If you want to incorporate some hard constraints that are important, you can do it. It's generally a problem of engineering, let's say, of figuring out how to code it efficiently and so on, more than a theoretical limitation. And you have flexibility on what I was saying of the proxy. You choose your property, and as long as you have a model that makes predictions on that property and they are kind of not too bad, you're going to have an efficient method to generate good candidates. And that shouldn't be the end of the story. So that should take us to the beginning of the presentation, where I talked about this active learning loop, where the idea is that you have a generative model that generates candidates. The candidates are not going to be perfect at the first iteration, but the good news is that this is fast. So you take these candidates, maybe verify them or reevaluate them with your DFT, generate more data, retrain your models, and check again, and so on. And the idea is that this should take us closer to what we want.
Mm-hmm. And GFlowNet can be put on top of, like, I don't know, Orb or Mace neural network potential models. Yeah.
And this is actually, in fact, what we are currently doing.
Okay.
You can use Mace. Mace in particular would be the proxy model, the reward function of your GFlowNet. So it would be, if I go back quickly, Mace could be proxy model.
Okay. Yeah.
And GFlowNet would generate proportionally to what Mace gives you. So if Mace is good, then GFlowNet should learn to get good stuff as well.
Yeah.
That's the idea. Why Mace and not Orb? I don't know.
It can be any.
That's the thing. That's the point I'm trying to make. It's flexible. This doesn't depend on a specific choice. If you have a good model that you've built or that your colleagues have built, you can go and use it. That's the kind of one of the advantages of this method.
Okay. So I think it's 12:30. If you have maybe any other questions, I think you can email Alex. With all that said, I'd like to thank once again Digital Research Alliance Canada for sponsoring this project. And of course, I'd like to thank Alex for bringing us an introduction to GFlowNets. Finally, I've understood the differences and nuances between this and generative models. So I'm happy because it's a big Montreal invention for us here. Yeah. So thank you very much. Thank you everybody for attending. Alex, when you get the chance to just fix that bugs like they're saying here, the installing 1.26 for NumPy, I've had those errors too with Quantum Express, so it's a pain. But I will share that with everybody that had joined the event and on the YouTube. I think that's where we'll end. Thank you very much, Alex, and thank you everybody for attending.
My pleasure. Thanks everybody. I apologize for the technical glitch. Yeah, I'll fix it for you to play with the notebook later. Take care, everybody, and feel free to get in touch by email.
Bye.
Goodbye.